I'm Brian Ben Straalen. I'll do my own intro. Yeah. I'm from Lawrence Berkeley National Laboratory. I do mostly my day job is doing new numerical algorithms, doing adaptive mesh refinement, and being involved in several DOE science application areas. One of them being astrophysics, but also do stellar physics, Earth modeling, subsurface work, a lot of different modeling areas. But mostly partial differential equations, mostly doing finite volume methods, and mostly doing structured adaptive mesh refinement techniques. And that's not what you're going to hear about today until the very end. So this was a speculative grant I put in. I still don't know if I'm going to get it or not. But looking back at compression as a way of mitigating some of the problems in transitioning to the exascale. So we look at basically what drives both the capital costs and the energy costs. So we've said that big machines are expensive and big machines cost a lot of energy. What is costing all that energy? A lot of it is doing volatile memory refresh. A lot of it is the caches that are sitting on the machines. Cache memory on the node also dominates a lot of the cost of printing the chip, keeping all the disks running, keeping the entire machine cool. These are basically what dominate installing a machine's costs, both the capital costs and the operating costs. And it's all about how much data you have. It isn't really about what your calculations are doing. So go. And where is it going to go? So if you want to get to an exaflop, so we got tasked with, I've been on these exascale workshops now for ages, and we basically get given the double requirement of you need to make an exaflop and you got to do it for 20 megawatts. So you can do a little back of the envelope calculation and you realize, I can only really spend about 1 megaflop. My total budget for doing D-flops needs to be about 1 or 2 megawatts. And then you got to, then you add the times 10 multiplier for keeping the rest of the machine on and doing everything else that has to happen. So you can see I can, at 100 picojoules for DP flop, you're not going to make it. It's going to be a 200 megawatt machine. So they just said, well, it can't be 100 picojoules. It has to be 10. And they'll do, come hell or high water, they'll make a 10 picojoule double flop. And they're on track to get there. And you can't be talking to your registers at 2 or 3 picojoules. You need to get that down to maybe 2. So you gotta get that down. You notice the rest are remarkably stubborn. These ones don't want to move at all, and these ones move. That's a large jump, right? We went, this is a log scale. We got big savings, but these are still very high numbers compared to all of these numbers. And this number is very tiny compared to this number, and this number is very tiny compared to this number. So, you really can't do much about this. You're talking about 11 nanometer technology, where I can't really play the voltage much, and most of the energy loss is from leakages. So it isn't really getting the latch, moving the latch, pushing the latch, doing the transition on the transistor. It's the leakage from the main, from you have the little negative guy that goes in the transistor, and you have the bleed off. That's where most of the power is going in this environment. So that's also going to be very stubborn. So you kind of look at how machines are built these days. You can see that, so RF is register file, L1, L2, L3, local data, network data. And you can see this is the bandwidth I tend to get, and the bandwidth basically matches along with how much energy these things take. And that's because your network data and your local data are of much larger scale. If you kind of balance out how much energy goes to the various subsystems, they need to drop like this. So things that improve latency tend to cost us much more memory. Much more energy. So things like things at high latency, like prefetch, load value prediction, speculative execution, all these things that kind of make your tolerate latency also cost lots of energy. So don't count on seeing a whole lot of it. We're going to think very carefully about what of all of these techniques we're going to be using in order to kind of stay under our energy budget. So basically it boils down to you're going to have wide vector units. Your logic unit pipeline is probably already at the minimum it's going to get. The clock speed is going to be what it is now, maybe a little lower. Many more cores per die, about 1,000 times more parallelism within a node, but maybe double the bandwidth to memory. So I need to get 1,000 times more processing power with maybe doubling the bandwidth and maybe halving the latency into those cores. And it's going to happen fairly fast. 2018 is only a few years away. We're going to start getting machines that look a little bit like the precursors for this, probably in 2017. We'll probably get experimental versions of this in 2018. So that's not very far away. And I can look at my code base and think, I could probably find 1,000 times more parallelism in my code. I really could. I have a fairly coarse-grained parallelism. I can push my granularity of my parallelism right down to the stencil, right down to the point by point by point. These things are independently calculated or have a local synchronization involved in them. So I think I could do this. But can I do this with maybe only 5 times total memory available at all? Right? I need to do that same so you give me 1,000 times more processing, but you're only going to give me about 5 times more total memory. Right? I'm going to get exascale computing with petabytes of data. So the question is, can I still get science this way? So maybe compression can be used here. So lots of codes currently maybe run at 4% to 10% of the machine peak right now. And the rest of the time, they're waiting around for the memory to show up. So we can probably give up a lot of the on-node compute performance in order to mitigate this kind of falling off the cliff that most production codes are walking into right now, which is they're going to go from a 4% peak to a 0.04% peak if they kind of continue with process as we're going now. But compression has been tried before, repeatedly. So why do I think it could be better? Why do I think it's going to work now as opposed to before? So first I'll define what I mean by in-situ compression. So you have far memory, and red implies it's in some kind of compressed, unintelligible state. It comes into the local memory. It is expanded out to its real size. Now you have real floating point data. Various operations are done on it through various arrays. I have multiple outputs, perhaps, and that I compress in local memory, and those go back out. So in terms of the cost for latency and the cost for energy, it's those big spikes of off the die, off into the DRAM, or onto the disk, or into the network, where this size of memory, this is the kind of bandwidth I need, not this kind of bandwidth. So that's just for definitions. So this isn't a unique definition. So Power 7s and Power 8s provide what's called active memory expansion. So idle pages get compressed. So those lets you simulate as if you have a larger DRAM machine. So you go to IBM, you buy a machine of this size, and IBM says, well, you have to install this much RAM, but I'm going to let you pretend like it's an even bigger RAM machine. You go, more RAM, awesome. I love you, IBM. I'm going to give you my money. In terms of our world, though, it hurts you in both legs. This creates a more latent memory, and it's actually more energy intensive to use this memory because it's going to be doing it kind of automatically. So you have to have a process running. So you have a coprocessor, there's a chip on that board that's running this algorithm and putting it in and taking it back. So it's not surprised that mostly when Power 7 has been installed in various facilities, AME is turned off. It really shows up in the performance. So for database people, maybe this is okay. But for if the alternative is swapping, then this is a lot better than swapping, right? So if you're really up against the end of the RAM on your workstation or on your processing system, and the alternative is I buy more memory or I buy a bigger machine, this can really extend the life of your machine. There's also doing MPI compression. So for messages over a certain size, you compress it and send it, and the gains you make, I can compress it faster than what it costs in terms of bandwidth. So I win again that way. And there's I/O compression. We have lots of different ways of doing compression for things that go out to disk. You can do compression as it's going out the disk. You can compress it once it's on the disk. I can have fast disks where things go out quickly, and then I can compress it when it goes up to the tape archive. So now on the last section there, which is called ND, there's another column there called deep archive or disk. And at that point, you've already crossed the line. Everyone's doing compression of various kinds on that technology. And now the networks are looking at doing compression at this level of the hardware stack. So when does it move up into the die? So there's also been things like load store compression, where you have a load and you have a store, and if it's a load or a store of 64 bits or 128 bits, it says, oh, this is probably floating point. I'm going to run a hardware-based compression scheme and decompression scheme. I'm going to do it for everyone that's of that size. So you can do it very fast in hardware, but it's not really efficient because you get very poor compression ratios because you lose too much of your context. The hardware knows very little about what that data is all about. Its predictors are quite low. Good compression implies good prediction. So data that's predictable is compressible. So you have to maintain some level of low entropy, meaning high predictability implies high compression rates. But at the level of the instruction stream, too much context has been lost. Right? You don't really know what arrays have correlation within them, which one is just the time step, which one's just, I don't know that this time step load has to correlate with the time step that was way somewhere else in the execution stack. So the hardware's already lost the connection between who got connected to what. So you lose the predictability. So as a reminder, I'll go through what a floating point representation is. So floating point compressors, make use of at least this fact that I have exponents are going to operate very differently from the fraction part and the sign bit. So you break things apart in terms of if I just take a stream of floating point and just break it into its fraction point and its exponent part, the exponent part is highly predictable. So as a stream of exponents are coming through, I'm either going through structure of arrays or array of structures, but repeating patterns are going to keep happening, and the exponents change slowly. And similarly, numbers that are near each other in terms of, if it's spatially varying data, then, short of having discontinuities or shocks or strong nonlinearities, you're going to have a lot of regularity in these bits as well. So, FZIP and other floating point compression schemes make use of that. So that's context, right? This is context that even the instruction stream didn't see. It just saw move 64, and it could guess that that was a floating point, but it could be an integer now, right? Or it could be a pointer. So it really doesn't know what 64 bits really is when it comes to the instruction stream. In particular, the microarchitecture has no clue. So you go past the instruction set into the internal micro-ops, it can't see any of this. So this is for a previous talk, but basically B-area entropy is, what's the entropy if I know more about the previous states? So create more context. So the classic place where you create more context is things like in an array of data. So here's an example of a 1D array floating point compressor. So Martin and I are doing work on alternatives to this, but you have basically, there's some context. So an FCM is a finite context method where it's keeping track of so many previous guesses that have been made. And the DCM is a differential finite context method. So it's taking differences of myself and the next one and keeping track of a context state with that. And then it does a little kind of predictor selector based on which one guessed closest. So it does an XOR with what the data really is. And it takes whatever bits didn't zero out with the XOR and says that's what's going to get sent into the output stream. So the degree to which you can predict based on the previous values is the degree to which, that's how many bits you got to drop into this. There's a little overhead with keeping track of where one word starts, the next word starts. But you can get good compression with this kind of technique. And just basically, this is a kind of a lottery between two things. And there's one bit that says which one guessed better. So in this case, you have two what I call composable compression modules that are being paired up in an XOR. And then there's an extra bit that keeps track of that. But there's different ways we can do this. We could have chained them. So I could have had the FCM could feed into the DFM, and then you could have other ones. So we have a whole family of these types of finite context predictors. It's fast, but it's not good enough. So for some data sets, this can get like 10x compression. So if you take we did a data set involved, this is plasma in a tokamak, so it's mostly a kinetic code, particle code. And with that one, it can get about 10x. But then, some of them, and this can run very fast. This entire algorithm you see, I can do in only like 35 clock cycles to be doing this entire algorithm. But for some other ones, plain old gzip worked better. Nothing runs as fast as the FCP. This one's basically the fastest you can do. But context is, in this particular example, the only context I said is the numbers following each other have some importance, and there's some relativeness between them, and I'm going to try to exploit it. I don't know how I'm going to exploit it, but I'm going to try to exploit it. So, so is that number of cycles good? Is 10 good? Would 2 even be good? So you have to kind of figure out, the later part of the research is involved doing more of that. So FPC is just a tournament scheme. What you want to do is you have a larger variety of these. Chaining them can get you higher compression rates. You can assemble these in compress and decompress. If you make them reversible, then it's easy to build up a chain of composable compressions and then know what the decompression is and know that it's going to run just as fast as the compression did. Eventually, we'll look at taking source code, instrumenting source code, having a compiler or something like Rose do auto-conversion to create where in the code I want this level. And this also lends itself to pipeline parallelism and over-decomposition. So there's no reason that, over-decomposition takes out some context, but it gives me more parallelism. So I got to trade off how much over-decomposition I do versus how much context I'm going to be wiping out. There's a question of, can various threads share their finite state machine? So it might be that I can create a very large finite state machine that several threads are sharing. But then you have contention. So you have to figure out how tightly can they interact with each other. So, so this is for Myra. This is a Blue Gene Q architecture. And you just have this is just doing streaming. And you say, this is 2 threads on the entire die doing stream. And then up here you get 4 is the blue, and 16 is this cyan here. So in terms of the L2 and the DRAM, L1, L2, L1 bandwidths, so there's this spike that comes up this way, which is there's context overhead of the threading that's more expensive than the actual moving data. Then eventually you get enough threads running where you saturate how much bandwidth can actually be moved through your L1. And this is saturating how much data can come in and out of L2, and this is saturating your DRAM. So this vertical axis is bandwidth, and the horizontal width is stanza size or data size you want to move through it. So you really can't, this is the working set. So once your working set gets larger than L1, you spill. Now you're talking to the L2 a lot. Then once you get bigger than the L2, you spill out of there. And now you're talking to the DRAM. So I only need about 2 threads out of the 64 threads in that machine. And I ran this in layout 2. So that means, thread 1, 2, 3, 4 goes on one core. 4, 5, 6, 7 goes on the next core. So this 2 threads here is 2 threads of one core. Can already saturate the DRAM access time for this processor. And I can already saturate my L2 and almost my L1 just by loading up one core. So one core is enough on that machine if you just let it do loads and stores to completely use up all your available bandwidth. So if you wanted to write programs like they teach you in their workshops, they would say, well, you want to do a mixture of computing and loading, and I can have so many outstanding loads going, and I can have so much compute going. But at steady state, I really need at least 16 instructions being dispatched per load that I make. Almost no one's code really has a 16 operational intensity or arithmetic intensity, right? And that's not counting the store. So we're already at machines now installed in production where we really need to rethink and reconsider, maybe 2 of the cores here really should have been pulling compressed data out of the DRAM in the L2 and loading up uncompressed data into L1, or loading up uncompressed data into the registers. So there's a question of how you implement this, but I think the technology already, I have a similar calculation for Ivy Bridge. So even for Ivy Bridge, if I take one of its cores on that node and do the same experiment, I can saturate DRAM in L3. L2, I need a core and a half. So I have a lot of capacity sitting on that processor that's never going to get used. No one's code is going to get much, so they're going to, if you run basically the mode they want you to run in, you're going to get maybe 2%. So can I bring you back up to 8%, right? So can you give up 8% of your cores on that die to do the compression and decompression algorithm? And I can get you back up to where you were in terms of productivity. So maybe not. So in terms of charm, I would consider this to be like a compute-intensive prefetch. So uncompressed data can be done locally and forwarded. So if the chars are in a kind of a local data context, they get moved around in their uncompressed state. If someone's remotely asked for it, well, now maybe it goes back into compressed. So you have to decide, where's my compression wall? Is it at the pins? Is at the pins, then nothing ever goes out to the NIC or the DRAM or the disk, if you can really do it, in an uncompressed format. The question of how this interacts with the granularity of the paging system. And yeah, you can do a lot of compressing until you exceed your local working set and you start spilling yourself back out. So you have to kind of have a very, part of what I worry about is, do I need scratch pad memory to make this work? So, if I create a local, if I have the blue array that I've allocated as memory, and say I start overusing my local memory space, or just I have a conflict miss. So that conflict miss on my blue memory, I have to have somewhere over in DRAM that memory is a friend of, right? Cache is just an artifact. It's really memory. And the fact that it's local is just the fact that what's going to happen is it's going to push it all the way down, spill it all the way back out to DRAM. So if my blue objects get spilled out to DRAM, I lose. So the only way I can think of to really prevent that is I create a memory map, or I create a scratch pad of some kind. So I know that on Knight's Landing, I'm going to get some level of controllable scratch padding. So I can turn some cache off and say I'm going to directly address some of this memory as its own memory location. So I can truly have L memory, local memory. So hopefully I can manage, but I'm going to need something like charm++ to manage this this local store. Because all the guys are going to be coming in, so I have like a little local heap that has to be worked on, as well as my far heap. And go. So I'll be working on the DOE proxy apps. So there's the ones out of the co-design centers. There's the Mantivo proxy apps. That's one out of the Sandia group. And my own code base, which is Chombo. Basically, the first phase of all this is doing a lot of instrumentation and a lot of measurement. So you can calculate on a particular data section and a particular, in a location in the call graph for a particular load, store, or memory traffic access. You can identify, that's your tag, and then you say, how compressible is this location in the data stream? So you run an arithmetic encoder or an entropy encoder on that data, figure out what's the maximum compressibility I could have gotten. If the answer is, this is pretty random, jumbly data, you don't put any compression in that location. But it has to be a cooperation between this kind of memory, this compression profiler. The source code has to be modified in production mode to make use of this. You need and then you need to run a auto tuner to look for the correct combination of composable compression elements so that you can do this kind of compressed prefetch and store operations. So I need a runtime system of some kind. I need probably what's not in there now. And this might not get, based on the experimental results, this might not happen. I might go through all these codes and discover there's no there. There's not enough compressibility given this current generation of machines. It's going to cost either the data is not very compressible, in which case the gains are too small, or it's compressible, but it's going to cost you, half of your compute access on a whole current mini-core processor to do it, in which case you pay too much of an energy cost. Right? It's going to cost you too much power to do the compression and decompression. So I can stop there. I have other slides, but I'm guessing if it comes up in questions, I can jump to it.
Let's thank our speaker. And we have time for questions.
Isn't latency sort of a lower level priority? I mean, what you really want is flops per joule or something, right? And having short latency can just increase the consumption of energy to no good end.
So you think that, well, the point here would be that you've pipelined yourself in such a way that there aren't idle units waiting for the data to show up. Right? This really is all premised on the idea that you really have done a just-in-time decompression. So if you can't manage that, so I request it, now I'm going to go figure out, I need to go to this location, do the load, add more time before you get it, and you're sitting there idle. That's not going to work. So you really need much smarter. It has to be integrated in some kind of smart prefetching, so that when you come to do the instructions, it's already in there and decompressed and local. So that's, engineering-wise, it's harder than it looks.
I'm not sure I understood your numbers. I think you're telling me that the fastest I can get data is about 16 instruction cycles. So suppose I'm pretty numerical heavy and I need 5 cycles to process a word. So that means I have 10 cycles to spare.
Yeah.
So if your compression is more than 10 cycles per word, then I've lost, right? Because you now have delayed my access to the data by the excess. And so you were suggesting 35 cycles in a particular example. So
on those cores where I was just doing loads and stores, all the other units were sitting idle. The processing units weren't running, right? So I have a QPX wide integer pipeline sitting there, not being used right now. The cores that are doing the loading will also run. The other 15 cores can just compute.
So I should take the 35 instructions and divide by 15?
You should divide that by the 15 guys who are supposed to be doing that work with it, yeah.
So it's effectively 2 or 3 instructions, okay, out of my 16.
You got to spread it around, yeah.
Okay, thanks.
And I don't think Myra's the last processor in this chain, right? I think the next one is going to have parameters that look even harder on us.
So in fact, scratch pads and controlling them through prefetches is something that we can do in CHARM. We have done that for cell processors, and so this will be a good fit to explore in some simulation environment. The question I have for you is, would this stuff go away with something like HMC? I think a whole lot of the trade-off here is the fact that if you are limited by the memory bandwidth, then your compression can cure that. Of course, otherwise it adds latency, and so. But if you're limited already by bandwidth, then might as well compress. But if you're going to get a huge amount of bandwidth boost through this data cube 3D stacked memories that they're talking about, then does this go away?
Well, there's other ways that there's many ways this can go away, right? So first, I can stack some amount of memory on top of my die, but it all has to be a low power now, right? I can't stack a high power memory on top of a high power CPU set. So everyone has to come down in their clock to do stacking. So I have a stack processor back in LBL. It's an ARM processor, and it uses 2 watts. That's how you have to do it if you want to do stacking. So currently, I haven't seen anyone solve the thermal problem with stacking yet. But let's assume they do, right? They put a very big heat sink on top and just cool the whole damn thing. You will get very access to your local 16 gigabytes. But you still are going to have at least a factor of 5 to 10 on the board, which is just your regular DRAM, your less expensive DRAM. So you have to make the decision. I would consider that an on-pin decision. So that's on-core now. So I have a large HMC stacked memory on-core. I'm going to say I'm probably going to use that as where I'm going to do blue data. Red data is going to be even further away. So it's the stuff on my board and it's the network, right? it's possible, right? I'm still thinking that, if I turn L2 into a scratch pad, I might start actually, if I know about lifetimes, right? The ultimate goal is to just work on compressed data. So I want to write a new floating point pipeline, and then have it FPGA programmable, and just never uncompress it.